Batangas City, the capital of Batangas Province, has a total land area of more or less 28,541.44 hectares. The city of Batangas is a coastal city lying in a cove-like shape at the southeastern portion of Batangas Province. In the 2015 census, the population of Batangas City was 329,874 people with a density of 1,200 inhabitants per square kilometer, or 3,100 inhabitants per square mile. Despite the beauty of Batangas City, it also faces natural disasters that can lead to property destruction, such as volcanic eruptions, storms, and floods.
Dalawa pang bagong phreatomagmatic eruption ang naitala ng PHIVOC sa Bulkang Taal pasado alas 6 ngayong gabi.
Batangas City is also under a state of calamity due to Typhoon Quinta.
Ito ngayon si Ron Generoso, ilalapit ko yung kanyang mikropono dito. At Ron, ano nangyayari dyan? Maraming mabaha?
Yes po, sa above chest level po yung baha.
Naman, Batangas City, sinalanta ng matinding pagbaha dulot ng bagyong Rolly. Nasa 100 residente, inilikas. Ang sentro na balita mula kay Luisa Erispe, live. Live mula sa Batangas City, nagpapatrol si Jack Batallones.
Takot na takot ang anak ni Vanessa habang rumaragasa ang tubig sa labas ng kanilang bahay kahapon nang maglandfall sa lalawigan ng Batangas ang bagyong Rolly. Imbes na sa creek, umago sa kalye at sa bakuran ng tubig sa barangay San Isidro, Batangas City. Idinaan ng mga residente sa social media ang kanilang paghingi ng tulong. Agad rumisponde ang Philippine Coast Guard, Local Government Unit, PNP, AFP at Philippine National Red Cross. At pinasok ang Tierra Verde para masagip ang mga residente na natrap sa mga bubong.
Kaya niligas!
Flooding in Batangas City is one of the issues addressed by the Batangas City Risk Reduction Management Office. In addition, Batangas State University also has disaster preparedness projects that can help the community. Researchers from College of Industrial Technology, Graduate School, proposed a study with the Batangas City Disaster Risk Reduction Management Office to monitor the water level in the Kalampang River in Batangas City, entitled BAHA, Batangas City Hydrological Forecast and Data Acquisition System, which has 3 sub-projects. First, flood level and amount of rainfall monitoring system. Second, online flood monitoring and decision support system using predictive analytics. Lastly, development of disaster-related data transmission system using wireless communication technology for CDRRMO. The system is locally available for a variety of applications such as real-time monitoring, assessment of data for early forecast and proper information dissemination in the affected areas. The flood level and amount of rainfall monitoring system. This study attempted to design and develop a flood level and amount of rainfall monitoring system. Specifically, this research sought attainment of the following. 1. To develop a wireless sensor nodes that will detect flood level and amount of rainfall with considerations on the following aspects: hydrostatic level sensor and tipping bucket rain gauge. The initial stage in selecting flood level and amount of rainfall sensor is to gather information. on the CDRRMO's Kalampang River Flood Level Protocol and the BAHA Standard Protocol on Warnings, Classification, and Amount of Rainfall Measurement. After acquiring the government agency's protocol, different sensors for flood level and amount of rainfall were compared and examined. The hydrostatic sensor and tipping bucket rain gauge along Kalampang River are chosen for water level and amount of rainfall respectively. 2. To integrate the following wireless communication system for data network transfer. Long-range wireless area network, also known as LoRaWAN, point-to-multipoint, and wireless fidelity. In wireless communication between sensor and gateway, the ability to transfer data over a long distance is taken into account. The data will subsequently be transferred over a 950-meter distance to a gateway in Barangay Uno via the long-range wide area network, also known as LoRaWAN. The LoRaWAN data will also be converted to a Wi-Fi network. Likewise, the Wi-Fi network in Barangay Uno is responsible of data transmission to the Project BAHA server at Batangas State University's main campus over a 900-meter distance. On selection of P2MP devices for gateway to server, simulation software was used to assess several P2MP devices and came up with the idea of utilizing PowerBeam and LightBeam 120 for communication between the gateway and server. It can see that the path of gateway to server passed through a church with a very high infrastructure. This gave the researcher a big challenge to be able to have a line of sight between the P2MP devices. As a result, a 24 meters pole was installed on the top of the barangay hall, and LightBeam 120 were placed on the top of a 23-meter infrastructure at Batangas State University. 3. To design and develop a web-based user interface for flood and rainfall monitoring system. The online database makes the data accessible for the purpose of real-time monitoring via graph demonstration. To test and evaluate the system's functionality and performance relative to the following parameters: accuracy and reliability, hydrostatic level sensor and tipping bucket calibration, LoRaWAN signal strength test, Wi-Fi and P2MP connectivity and system reliability. online flood monitoring board and decision support system using predictive analytics. The study aims to develop an online flood monitoring and decision support system using predictive analytics. Specifically, the study aims to attain the following objectives. 1. To design and develop an online monitoring interface, considering the system-generated flood forecast using predictive analytics. An online visual map of the sensor locations signposted with flood alert level. The study used random forest for classification of flood alert or flood advisory level. In training the model, the study used 3 years equivalent of 139,137 DOST PAGASA historical data. This covers the years of 2018 to 2020. In the preparation of dataset, DOST data are scaled to proportionate with the data to be used by the system. This is to compare historical data to current data values. To validate the comparison, several actual water level measurements were taken. 5 trials of actual measurements were carried out and consistently resulted to 9 meters variance. Obtained variance will be deducted from all historical data prior to training. From the historical data of DOST, adjusted data in centimeters value, water fluctuation rate per 10 minutes, water fluctuation rate per minute and flood advisory level are assigned to the values. The model was developed using Python programming combined with other libraries and functions like Pandas, sklearn, NumPy and trend function for data analysis. The algorithm will run every 10 minutes after being integrated to the online system, allowing for the generation of periodic forecasts. Classification model, current data and trend analysis are the necessary component for predictive analytics. Classification model is a factor of the prediction process that will categorize current data according to the degree of flood advisory level it covers. On the other hand, trend analysis, which reflect the smooth, long-term, average tendency, are used to determine the general propensity of data to climb or decrease over time. These entities are required for the generation of the periodic forecast. This forecast is saved in the system's database for future reference. Upon utilization of the established prediction model, the system has the ability to make a forecast using current water level data. This is through combination of classification model that determine the flood advisory level of the current data and the trend analysis of the water variation of the past 10 minutes. This trend is graphically represented and included in the graphical user interface of the forecast bulletin. The study made use of the PHP programming language for web development, as well as an API tool to display the map into the online graphical user interface. The study used the functionalities of Google Maps API provided by a JavaScript library located at Google. Flood advisory level was expressed by map pin color. 2. Verification of the real-time water level status through the integration of digital video camera. Based on the perspective observed in the real-time view of the camera deployed at the location, CDRRMO can verify if the data obtained in the flood sensor reading graph is accurate. Current water level can be compared to what was observed from IP camera installed at the location. Comparing sensor graph status and advisory bulletin versus real-time view via IP camera are means of verification to check the forecast's accuracy. 3. To generate and provide the information on place based on sensor location, time, current and predicted alert level and mitigation measures. Combination of PHP programming and implementation of the established prediction model, the developed decision support system can generate the information of place. Place are determined by the identified location where the flood sensor is installed. Each flood sensor has a corresponding location in the flood sensor map. Place are identified by location coordinates, as well as the name of barangay where flood sensors are installed. On the other hand, there are 2 types of time that can be seen in the forecast: the time when the forecast is generated and the time when the water will reach a certain level. Moreover, Two types of flood advisory level are also evident in the forecast bulletin. This is the current flood advisory level is determined by the current sensor reading, as well as the anticipated flood advisory level based on the trend of water level variations over the previous 10 minutes. Lastly is the generated mitigation measure. In this study, mitigation measure is in the form of advice to the monitored community to prevent, reduce or control adverse effects of possible flooding. Hyperparameter tuning was used to test the model's accuracy. This was performed by the trial and error approach of adjusting the number of trees in the forest. Changing the number of estimators was used to achieve the optimum model accuracy. Based on the accuracy tests, it's noticeable that setting the estimators too high results in a significant percentage of RSME. As a result, the study chose to employ 100 estimators with a 99.57 accuracy, with RSME percentage of 6%, as model accuracy is considered excellent, when RMC is less than 10%. As part of development, testing the models in various scenarios using simulation approach will measure the system's performance. In this study, the researcher uses 4 to 20 mA simulator to represent the water level values transmission to online system. Significant water level fluctuation was observed on July 24, 2021 starting at 7:30 a.m. Details of the actual and predicted water level can be found in the summary. It will be noted that the generated prediction is not far from the actual outcome considering the measured water level. It can be considered that the prediction model has been effective in making a forecast based on the trend of water level fluctuation of the 10 minutes recent historical data. Development of disaster-related data transmission system using wireless communication technology for CDRRMO. The study aims to design and develop a system for disaster-related transmission using wireless communication technology for CDRRMO. Specifically, the study aims to achieve the following. 1. To integrate various types of wireless communication technology for information dissemination using the following. Wireless fidelity, global system for mobile communications, long-range wide area network. This study, various types of wireless networks were combined to further expand the network for sending disaster information to the community. Wi-Fi is used to receive and transmit data from the sensor nodes. The study has 3 topologies used to produce a hybrid network topology. 1. Mesh topology. 2. Point-to-point topology. 3. Point-to-multipoint topology. The network has good result of connection, with 288.36 megabits per second speed from the access point to 134 megabits per second speed in the station. The Wi-Fi networks that were utilized to receive and send data worked as expected. The study is also capable for receiving data via GSM in different projects like Seagull, but the study requires keyword to process the data. The GSM module in this study has 2 processes. It involves receiving data from the wireless sensor nodes and sending information from the admin to the client or user via the system's SMS text blast message. In this study, long-range wide area network, also known as LoRaWAN, was utilized, which does not require any loading like mobile data, e-load and internet. LoRaWAN and Wi-Fi module is integrated into the MCU setup so that it can connect to the wireless network. The administrator has control over when the alarm goes on and off in the web-based system. 2. Developed web-based system for transmitting and receiving data with following consideration. Local area network and wide area network. The system is developed in a local area network. The researcher used a Linux-based router which used to modify the computer system into a reliable network router. This router has all of the essential system functions, including routing, firewall, bandwidth control, wireless access point, backhaul link, and hotspot gateway. The researcher used a cross-platform application that enables system to expose a local development server to the internet with minimal effort. The locally hosted web server appear to be hosted on a subdomain of cross-platform application so that users can also view online and the administrator can access the system online through the internet connection. 3. Disseminate of information in multiple platform, SMS text message, Facebook API, Android messaging application and warning system. Batangas City Hydrological Forecast and Data Acquisition System incurred an estimated total project cost of 401,550 pesos. This covers the cost of all hardware components, communication infrastructures and devices, monitoring equipment and miscellaneous expenses. To test the performance and functionality of the entire project, the corresponding hardware and infrastructure have been built and installed at strategic locations along the Kalampang River.
Halos social media ang ginagamit po namin. Tapos
Ibig sabihin,
sa pagdala, yan.
masisensya mo na kayo.
Direct na hanggang office ng disaster.
So, siya ay sabi may daan ng sabi.
Likewise, monitoring equipment was endorsed to the concerned agencies, CDRRMO and the involved local government unit so it can be utilized as a fully operational system.
Hindi mo yung bro na nag-work sa monitoring ng river ay narito na sa bala na kaunti. Para lang po, ang kay Sir Aldo po, ang charge po siya dun sa pag-install ng mga sensors at saka pagbabato po ng data tungkol sa ating system, sa ating online system. Ang part ko naman po is yung part ko na decision support system para mag-develop ng algorithm wherein ang kay Sir Ed Central na naman po, siya naman po in charge. Just in case naman po, we have to tell the community na to evacuate from the locality kung nasan yung baha. I think si Sir naman po ang in charge. Ayun yung system ng development na imanagin po dito just para pag na-testing is yung
It aims to record feedbacks from end users and continue to validate its accuracy to further improve the developed system for more accurate outcomes.
Una sa lahat ay ang aming pasasalamat sa pamunuan ng Batangas State University sa pamumuno ng responsable at napakasipag na presidente, Dr. Terso Ronquillo, at sa grupo ng mga professor na sina Professor Gina Eje, Professor Edser Toralba at Professor Albert Villena para sa pagbibigay nila ng oras, dedikasyon at prioridad upang makalika ng isang teknolohiyang makatutulong sa pamahalang lungsod ng Batangas at sa kanyang mga mamamayan. Ang Batangas City Hydrological Forecast at Data Acquisition System na kanilang inbensyon ay isang innovative system kung saan tulad ng existing flood early warning system or devices ay may kakayanang mag-detect ng pagtaas at pagbaba ng level ng tubig. Ito ay makapagbibigay ng early warning upang mas maaga makapaghanda ang populasyon at risk na nakatira sa low-lying at flood-prone areas ng Batangas City na matatagpuan din malapit sa Kalumpang River at sa mga daluyan ng tubig. Sa kanyang kakayanan na makapagbato ng impormasyon sa Disaster Operations Center, mas mapapadali at magiging mas akma ang aming mga desisyon na aming gagawin patungkol sa pagtugon sa mga pangangailangan. Sa pamamagitan din ito ay mas magiging madali ang pagmonitor ng pagtaas ng tubig at mas magiging maagap ang pagbibigay abiso sa mga pamilyang nangangailangang lumikas. Ang kanyang surveillance camera or CCTV ay makapagbibigay ng mas accurate at real-time monitoring na magiging accessible sa Disaster Operations Center sa pamamagitan ng kanilang website. Dahil gumagamit ito ng pressure sensor ay may iwasan na ang mga false alarms. Sa pamamagitan din ng website para sa system na ito ay makikita din ang mga graph para sa flood sensor at rain gauge sensor na mas madaling basahin at maaaring gamiting basihan sa pagtataas ng mga alarma. Ang isa pang kapuring parte ng proyektong ito ay ang BAHA messaging tool na nagpapadala ng update at advisories ukol sa nade-detect ng sensor. Naniniwala akong ang proyektong ito ay lubhang magiging kapakipakinabang sa pamahalang lungsod ng Batangas at sa aming mamamayan sa panahon ng kalamidad. Naway magpatuloy at mas sumibay pa ang partnership at collaboration ng Batangas Government at ng Batangas State University sa aspeto ng disaster risk reduction management para sa mas mapatibay pa ang kakayanan ng buong lungsod at may sakatuparan ang mithiing patungo sa mas ligtas at disaster resilient community. Again, maraming salamat po at mabuhay ang Batangas State University, mabuhay ang lungsod ng Batangas.